Hello everyone, welcome to the Builder Track. So I'm Muskan Mangla, volunteer in the OWASP community. I'll be moderating this session. During the next 45 minutes, you'll be listening to Dr. Luca and Feras present web developers beware of the Tarpits for SAST in your code. Please submit any questions you have during the session in the QA tab, just to the right of the video in the Hava platform. I'll be asking Dr. Luca and Feras your questions in the last 10 minutes of this session. Please note that the chat function in Zoom for attendees is disabled, but you can leave your comments and chat using the chat tab in the Huava. Well, I'll introduce the speakers briefly. Dr. Luca is a part of the security research team at SAP, where he is contributing to the research strategy and to the software security analysis area in particular. Feras is a PhD student at SAP University doing his research on the web security domain. In his work, he focuses on the static application security analysis to point out to the difficulties of these tools and the solutions to have better coverage of the source code. Now handing over to the speakers for this session, and over to you, Dr. Luca and Feras.
Thanks a lot for the introduction. I hope you can hear me well. Good morning. Pleasure to be here. Yes, I will share this presentation with Feras. I will start with the short introduction, context, etc. Then Feras will go into the technical details, and then I will take over for a few conclusion remarks. This work is also a collaboration with other security researchers. Julia was a former intern at SAP Security Research. Fabian is a chief scientist at Shift Left, and Davide Balzarotti is professor at Eurocom. And all this work is really, let's say, applied research, what you will see today, and is under an European project that is called Testable, that started last September, and what you are going to see here are first results coming out from that project. So if you like the results, please follow up on the, let's say, on the news in that project. Feras, if you can move to the next slide, please. Thanks a lot. Yeah, okay, this is the agenda. I already said I will start with some context, and Feras will take over with the technical details, because this is really something he did during his PhD that is still ongoing, but is really one first good mission he achieved in this PhD. And so Feras will present a motivational example, why it is important what you are doing, the approach that we developed, and then I will take over for some conclusion and next step. Next slide, Feras. Thanks. Okay. So the context is really SAST, Static Application Security Testing. So I don't know who is in the audience, but I would suspect that there are some developers among you, web developers. And so perhaps some of you has used these tools. But let me quickly say what these tools do. So essentially, imagine you have an application. It can be a web application, but it can be also any software application, right? Well, if you have the code, what you can do is to use a static analyzer, so a SAST tool, in order to analyze this code with the hope of detecting some vulnerabilities. So the code will analyze the code, will analyze the source code of your application. The tool will analyze the source code of your application, probably creating a kind of internal structure initially, abstract syntax tree with some additional relationship, maybe control flow, also some data flow, whatever, and then they will start navigating in this internal structure to discover vulnerabilities like cross-site scripting, SQL injections, others. However, I mean, you get findings from these tools. Sometimes you get false positive, and perhaps you analyze, you audit all the findings, you fix the true positive that were also reported. At some point, you reach a verdict that everything is fine. So you get the traffic light that is green. Okay, so now what is the conclusion? I mean, can we really say that everything was analyzed in your code and that there are no vulnerabilities? So are we really sure there are no false negative, sorry, in that application? So this is the kind of question we were investigating, knowing that SAST tools are widely used in industry. So we are from SAP. SAP is a large software company, and we use SAST tools internally to, let's say, during our software development life cycle, to verify, to analyze a program before shipping, right? So it's not the only tool that we use. It's not the only approach. We also have some dynamic analysis inside, but static analysis is for sure one of the means we use in order to ensure that our products are more secure. And especially when it is about injection vulnerabilities, these tools are believed to be pretty good. And actually, also in the OWASP code review guide, there is a version 2. I don't remember when it was delivered, but you have a link just below. And if you go on figure 1 and figure 2 of that guide, you will see a kind of survey that was done quite some time ago in 2015. But I don't think let's say, really the mood of developers that were participating in that survey changed. And they were really saying that, yes, indeed, SAST tools, they believe, is a good weapon against injection vulnerability. Feras, can you move to the next slide? But so, as I was saying before, so was all the code analyzed? Are we really sure that there are no bugs, no, let's say, undetected vulnerabilities, so false negatives that are just under-discovered? And this is the kind of question we have been investigating to understand, let's say, how good or how easy or how hard it is to do testing with the SAST tool. And how can we improve that testing if we can? Of course. So, and this is what we call testability somehow, testability for SAST. So how easy is to test an application with a SAST tool? What is that makes really difficult for a SAST tool to analyze an application? What makes it easy, etc., etc. So now I leave the floor to Feras to go into the technical details.
Thank you, Luca. Hope my voice is clear. So as Luca mentions, that what we are missing, or is what much confidence can we have with the static tools? And with you, I would like to go through an example. Sorry, I went to this. An example. So here we have an old CVE. And with this old CVE, there's a vulnerability, and the tool were not able to discover the vulnerability inside. But let us go to understand the path of this code, and then we will go more in more details. So here actually we can see that there's one line of code which is require once. So here is a PHP code, and require once in just including a file, and we can see the file it's a variable. So if this variable is controlled by an attacker, he can control which file will be included. He can do some manipulation here, so we will have a file inclusion vulnerability. So for that, we call that the sink. So we have the sink, and we need to check if this sink, there's a value coming from a source that's meaning a value coming from an external. So the user can control this variable, then he can control which file will be included. And then maybe the user will, it will be an attacker, which will manipulate here, and we will have the vulnerability. So if we go backward from this line, we can see that the act file is coming from this variable act, and it's coming from this gpc get string. Inside gpc get string, we can see there's this call user func array. In PHP, call user func array is just to call a function dynamically. So the name of the function can be inside a variable, or in our case, the name of the function is just defined here statically. So from this line, the function gpc get will be called. Sorry. So if we go to the function gpc get, we see that we have the post, which is the source. So we can see now that there is a path from a source to a sink, where the user can enter something, and then he can manipulate which file will be included, and that will call for a file inclusion. It's important to understand the vulnerability here to check then with the static tool. So we just take this vulnerable codes that we already discussed, and we scan it with static tool, and many of the static tools, they didn't discover this vulnerability. What is the main reason of that? We have a doubt that, okay, this call user func array, we are calling the function dynamically. What if the tool is not able to understand this line? and how we can check that. To check that, we just use something called the testability pattern. Actually, the testability pattern is very simple code. It has a source and it has a sink. The same as we explained before. The source is an input is coming from an external user, and the sink in this case it's an echo for the value that will cause an XSS, but it's not really important to understand what type of vulnerability here. But we just say, okay, we have a source and we have a sink, and there's a path between this source and sink. So now we will try to play around, try to make it a bit more difficult inside. We will inject our targets between the source and sink to check if the tools they are still able to handle these targets or not. And now in our case, we have the case of call user func array, and we want to test the call user func array. What we do is that we just simply with our patterns, we try to be straightforward, cover only the targets that we want to cover, minimize the code. So here we can see that we have the call user func array. We are calling the function f, passing an input, returning the input, and then we are printing it. So here there's the vulnerability. And we are sure that we don't have another target, only we have the call user func array. What about the static tools? When we scan this code with the static tools, we can see that 4 out of 6 in our arsenal that they were not able to handle this code and discover this vulnerability. And one of them is the commercial tools. We have 2 commercial tools in our arsenal. One of them is a commercial tool that didn't detect the vulnerability here. What we do is we try to transform the pattern. So here, actually, we are just calling the function. We are using call user func array built-in function to call the function gpc get, but actually we can call the gpc get directly. We don't really need to use this line. And then in this way, we are fixing the targets, and there's no targets anymore. But how we can be sure there's no other targets in the path between the source and the sink? After doing this transformation, we scan the code again, and then we found that the commercial tool is able to detect the file inclusion vulnerability in this code. That's meaning now the problem is solved, and we are detecting this testable target. It's important to point here the effect of the testability target. It could be just a simple line of code or multiple line of codes that they are blocking the flow for the static tools, and the static tools cannot cover what is after. In this project that we are discussing the CVE, actually, this function which is called gpc get strings, it's called many times. And every time the tool will, and it's always returning a source. Every time there's a call, the tool will consider that as a safe value, that it's not coming from an external user just because of one line of code that it will not able to handle. So we discussed the effect. Also, after creating our pattern, as we already saw, we create different instances. We try to make it a bit more difficult and check different cases between the tools. So we already discussed when the function is defined statically. What if it's defined as a constant inside the code? And if we apply constant propagation, we can know which function will be called. So it's the name of the function is inside a variable with instance 2, but actually this f variable is already defined before. And with instance 3, that we can know a part of the name of the function. So we can have, like, for example, here the function is f underscore, then there's something. So I can have a set of possible functions that can be called, which is f1 or f2. So that will help us to reduce the search space, and maybe we can focus only with these 2 functions. So now I will want to go. So after we discuss the effect of one testability target, I would like to go through our research methodology. Our work is divided on 3 phases. We will go deeply in each phase. But let me say that in the first phase, we create the patterns and we check them with the static tools. With the second, uh, we want to find their prevalence in the real projects. And in the third, we want to transform this pattern and see their impact on real projects. So let me begin with the pattern creation. For the patterns, we didn't want to be a language specific. We want our approach to be generalized. For that, we choose 2 different languages, which is PHP and JavaScript. For many patterns, there is a lot of intersection between the 2 languages, but it's also, it could have one language have more features than other, depending on the features that is providing, depending on the dynamicity of the language, or depending also how the tool is behaving with this language. Maybe the tool will be better with one language than other language. And because we want to be systematically with our creating for our patterns, we go through the documentation of the languages. We read the documentation, we check the corner cases, we check the discussion of the community about the difficulties of on some cases for the language, and we were creating the patterns. So we create 120 patterns instances for PHP and 150 instances for JavaScript. After creating the patterns, we measure them with our static tools. So we have some of the research tools and some of commercial tools. We can see that the commercial tools in most of the cases, they are behaving better. But overall, for PHP, there's no language support more than 50% of our patterns, while for JavaScript, they reach the 60%. Meanwhile, if we take the combination, that's like how many patterns that is not solved by any tool. So the combination can cover 66% of the patterns in PHP and can reach for 82% for JavaScript. So like that, we create our testability, our patterns library. But what if our patterns are just corner cases or just fancy features are no one used? Something that is not really exist, and maybe it's just like, okay, we can just ignore them. To answer this question, we went to check the prevalence of these projects, of these patterns in real projects. So we try to create a diverse data set of projects. We went to GitHub and we clone low popular projects, 1,000 projects that they have between 20 and 70 stars, medium popular between 200 and 700 stars, high popular 1,000 projects that they have more than 1,000 stars. Also, we found a website, it's called Source Codester, that is offering for the community an open source websites that they can use a part of the code, or they can use the whole code. So we combine this data set and we have in our data set 3,340 projects. After collecting the projects, we begin to use our patterns as a query inside the source code to search the occurrence of this pattern in this projects. And we found that our targets are highly prevalent. Actually, we will have 21 unique patterns in average per project. And we will experience one pattern every 20 lines of code. Just to explain here the graph that we have. So each point is representing a project. The colors is representing the sets that we have. As we said, it's a high popular, medium popular, low popular, and the source code ester. The Y will represent the number of unique patterns per project, while the X, it will more make me understand how many lines of code I will pass until I will experience a pattern. So for that, the X is the number of lines of code divided by the occurrence of all the patterns. So here is the patterns for all the tools in our work. But we already saw that the commercial tools are behaving much better than the research tools. So we focus on the two commercial tools for PHP, and we take only the the patterns that was not able to be solved by these tools. And we again see that our targets are highly prevalent even for the commercial tools. So the commercial tool will have in average 13 unique patterns in project, and we will experience one pattern every 47 line of code. While the other tool is a bit better, that we will have 8.5 unique patterns in average per project, and we will experience one pattern every 203 line of code. So now we see that the projects are highly prevalent, the patterns are highly prevalent, and we already saw the effect of one Tarpits, how much it can make it difficult for the static tool to handle. So now we can estimate that how much we are missing false negative when we are using the static tool, and we see that the tool cannot handle all the situations. What will be the main message of this high prevalence? I will return back to this point. But before, I just want to mention that we have a table in our paper explaining all the details about the patterns, the name of the patterns, the dimensions, the tool answer, and their prevalence between the four sets in our dataset. And we have this example. Actually, when I create this pattern, I was saying, okay, who will use this call user function array for calling a function statically, like if they can call the function directly. But I found that this Tarpit, it's used in 208 projects out of 1,000 projects in high popular projects that they have more than 1,000 stars. And to take the message from the high prevalence of our patterns, it will help the user to make them aware about the area of the code that can be confusing for the static tools. Instead of doing the manual work everywhere, they can focus their manual work in a specific area that the tool is not able to handle. Or maybe it could be possible to transform some of these patterns, and then it will be reducing the manual work for the developer or the security team, and we will have more, we will reduce the risk of having false negative. So how we will do this transformation, and how is the impact of these patterns? That's what we discussed in our last phase of our experiment. In this phase, we have the manual and the automated experiment. I just want here to say that, okay, we have the just to have a brief idea before we go in details. So I have the project. I scan it with a static tool, and I have my reports. Then I will do some transformation in the middle, and I will have another version of the project. I will scan it again. I will have a new another alert. I will compare between the old and the new one, and I will check the new one because the new one happened because of my transformation. And then I will have as alerts. The tool will give me, okay, this path is possible to be vulnerable. But in my side, I have to check if this path, if it's a true positive or if a false positive. So the manual pattern transformation. I went to an old CVE. I scan it with a static tool. If the tool couldn't find the vulnerability in this static tool, then I will discover the pattern in this vulnerable path. After I point the patterns, I will transform them in the whole project. So it's an old CVE. So we return to the version of the old version of the project when was this problem exists, and we take this version and we do the transformation on this version. After doing the transformation, we run on the static tools and we check the new alerts manually. At the same time, we went to the latest version of this project and we do the same transformation and we run with the static tools. So the problem or the vulnerability is already discovered before and it's already solved. So if we think about it, it shouldn't be now vulnerabilities in the latest version. But is that correct? I will answer this question in a few slides. But before I will go to that slide, I just want to say we did the transformation and we experienced 3 types of transformation. In the first one, we already discussed this one, it's semantic preserving. So actually the code is the same. I'm not changing anything. I'm just calling, instead of calling the function using call user func array, I'm calling it directly. In the second approach, in the second transformation, sorry, I need to apply over approximation. And here in this example, actually, it's just like we are forwarding the user from one PHP file to another PHP file by using a JavaScript. And the tool is not able to understand and parse this JavaScript to understand this flow from one file to another file. What I do simply that I delete this redirecting, and I did an include a normal in PHP. They are the same almost, but in PHP, when I define a variable in file 1, I can use it in file 2. So there's no problem here. But when I do a redirect and I define the file as a variable in file 1, and I will come to use it in file 2, it will be not defined. It will be an error. While in the third type, we need the developer help. Here, I need to explain a bit this pattern. So in this pattern, we already speak about the source and the sink, but here is the Tarpits here. It's a built-in function. It's called extract. Extract will take an array and will generate variables from this array. The keys in this array will be the name of the variables, and the values in this array will be the values of the variable. So here, the A actually will carry the value of AAA, which is the source. So here we have an XSS vulnerability. And when I was doing this manual work, I experienced a code like that. Extract post, and then an SQL query, and then I have username and password. From where this username and password, even for maybe a person who is reading the code, is difficult to know. So how the static tool will deal with that? Actually, this username and password are coming from the post. So here, we need the developer to do annotation to say, okay, this username and password are part of this post. Then if we look to the code, it will be very simple for the static tool now to discover the SQL injection in this case. That's okay, I have variables coming from the post going to SQL query without sanitization. So here we have an SQL injection. So in our paper, we work on 5 CVE for PHP, 5 CVE for JavaScript. We have all the details on the paper. We put the CVE number, the vulnerability in this CVE, the patterns that we transform, and the new alerts that we discovered. So for PHP, we transform 9 patterns, and for JavaScript, we transform 17 patterns. And in the vulnerable version, actually, after doing the transformation, we found 204 true positive real vulnerabilities exist in the vulnerable version after transforming these 9 patterns. The static tools were able to detect them, and 20 in JavaScript. So that was about the vulnerable version. While in the latest version, we discovered 6 new confirmed vulnerabilities confirmed by the developers and gains a CVE about them. It's an old CVE. We have an old CVE, and the problem is already known. And till the moment we are discovering these vulnerabilities because of these Tarpits. So actually, it's important when we receive a report from bug bounty or someone to tell us, okay, you have a vulnerability here. It's not enough to fix this vulnerability. I need to search for the reason why this vulnerability exists and I didn't found it before. If I'm using static tools, and the reason that is the Tarpits. So I receive the report. I go to the main reason, which is the Tarpit. I try to transform it, and then I run the tool again, and I will have a better coverage. I will have less risk of false negative. So this manual transformation done on just 10 projects. But actually these results give us the motivation to go to automated pattern transformation. For that, we choose 5 patterns that we say, okay, we will transfer them manually, automatically, sorry. We will transform them automatically on the data set that we discussed before, 3,300 projects inside. And we will compare the alerts before and after, and we will check the new alerts manually. So here just a table to explain that we have R1, R2 to R5 is the patterns that we choose, and we have their occurrence in each set in our data set, depending on the occurrence and the number of the projects. Then we have the number of new alerts that we found, and out of this new alerts, how many true positive we have. So in this experiment, we refactored 1,170 projects with the occurrence of 32,000. We had around 9,000 new alerts in 72 applications. Overall, we discovered 370 new vulnerabilities in 43 applications. Out of these 370 new vulnerabilities, 55 vulnerabilities in high popular projects that they have more than 1,000 stars. So we can see that just by transforming 5 patterns, that we have already around we have 120 instances for PHP, that we could have this coverage. So it's giving us it should be giving us an alert. That's how to work with the static tool, and it's of course it's reducing the manual work a lot, but still we cannot really say, okay, we are safe after using the static tool. And the Tarpits will help us and help the static tool to have better coverage. So we already discussed that we have many discoveries depending on 2 different experiments, manual and automated, that we did. We did the responsible disclosure for all the vulnerabilities, and we gained the CVEs, all the details actually about the manual and the automated experiments, about the CVEs, about the patterns. Everything is inside our repository on GitHub. So please feel free to go to there and check all the resources that we have over there. Now I pass again to Luca.
Sorry, just the time to unmute. Thanks a lot, Feras. So yeah, indeed, just to wrap up and to take the main takeaway messages out of this. So you saw that we created testability patterns, and we created those for PHP and more or less more than 100 also for JavaScript, 150, whatever. We saw that these patterns, that capture what we call Tarpits, so things that might confuse static analyzers. We saw that these Tarpits are real, that if you search for them in real application, you find them. And actually, I think this is also a very good added value of our work, because while we create a pattern that is a small test case for a SAST tool, we also create what we call the discovery rule. So what allows us to discover the pattern in real application, discover the Tarpit in real application. And then we saw that by transforming them, it's not always possible. Feras mentioned that there are these 3 types of transformation we identified so far. So it's not always possible. Perhaps sometimes we need help from the developer if the developer wants to, to help. But at least the developer will know that that part of the code will not be analyzed by the tool. So that is already quite important information, because it provides awareness, right? And we saw that by doing transformation, so by transforming our Tarpits, by removing our Tarpits, we were able to discover, to detect a lot of vulnerabilities. That was a very huge amount of work, especially for Feras. He mentioned about 9,000 new findings from the static analyzer. He didn't analyze all of them, of course. He analyzed, I think, 2,700. And out of them, he was able to discover 370 new vulnerabilities. And if you count also with the manual experiments, it's more than 400. And by doing the responsible disclosure, developers of this project confirmed that essentially what we were, let's say, auditing as true positive was a real true positive. I mean, and all in all, what this transformation show is that by doing that work, we can really increase the testability of the application when the application is tested via a SAST tool. There is also something else that we haven't done in our work that perhaps can be done, and I think we believe is something important for the community. So essentially, our Tarpits are available for the community, and if SAST tools wants to use them in order to measure what they support and what they do not support, and to see also what can be supported in the new release, perhaps, that is something that can be done. So what I'm saying is, from one side, you can try to improve the testability of an application by transforming, by removing the Tarpit. From the other side, you can try to improve the tool by making them supporting more Tarpits. So what are we working right now, and what are our next steps? So we are trying to enrich our pattern catalogs. One thing that we are doing is to focus on the Java language, also because this is a language that is very widely used, well, overall in the world, but also at SAP. And also we are, let's say, maturing our research, so we can see that our pattern schema can be improved. We can add other features to the pattern that are important. I cannot provide the details right now. We don't have the time. We are also developing a framework to operate this pattern. So we want, I mean, it will be kind of a database or file system based, but it doesn't matter. So we can create patterns. We can add those patterns in our catalog. We can measure those patterns against an arsenal of static analyzers, and we can discover those patterns in real application. And perhaps then we can also, have operation for transforming some of them in an automated manner. What we want to do in the context of this European project called Testable is to have, let's say, a tie with OWASP, and we are going to propose an OWASP project so that we can involve the OWASP community. We will do this by the end of this year, I think. And what we would like to do is our Tarpits are already available to the community, but we would like to make them more specific to the OWASP community, because I mean the web is the area we are targeting, and we hope that by doing so, the OWASP community can also participate, create perhaps some patterns on their own, and help the entire community to improve the results of the static analysis side. So if any of you is interested to use already now the patterns, get in touch with us, because the link that Feras provided that is in the slide is about the Tarpit we had at the time of paper, that is, let's say 6 months ago, more or less. So we have definitely updates that we didn't push yet because we are still refining the schema of the pattern, etc. But if you want to use them, get in touch with us. Perhaps we can provide anyhow the latest version so that you will not work with the let's say, an old version. But as I said, by the end of the year, with the OWASP project, I think we will deliver a good, stable version of these Tarpits. Can you move to the next slide for us? For us? Can you? Yeah, thanks. Okay, so get in touch with us. You have the emails here. I already mentioned this is a joint work with other researchers funded by an European project. There is a blog that we recently wrote. If you want to have a look, you have a link in the slide. Is a short blog. You can get a bit more details if you continue reading. But I think also if you want to say explain our work to others, that could be a good means. And if you want to have really full technical details, then I would suggest to go into our papers or just come back to us. And with that, thanks a lot for your attention, and we are open for questions.
Thank you, Luca and Feras, for the wonderful and amazing session. It was so insightful and very deep about the SAST and how you analyze the patterns, how you automated, and how you compare the tools. Very insightful session altogether. Now jumping to the Q&A, if audience has asked any of the questions. Yeah, one of them has asked, like, are you providing the slides? Where do you publish the paper, or do you have a link or any kind of information so that they can have a read of your paper?
I think the slides that we are just seeing is probably the one having those links. Just if you go in these two links, you will find the information that you were looking for. If there is anything else that you need, just get in touch with us. Not a problem at all.
Absolutely, sure. And the rest, I do have the queries. So I just wanted to know, like, basically, how do you discover your testability targets?
Okay, maybe I can take this question. So as we mentioned at the beginning, we have a joint work with the Shift Left, and actually they provide to us a framework that we can generate the code property graph about the source code. If someone doesn't know about the code property graph, it's a way, a data structure to represent the source code. When there's the AST, there is the flow between the data flow and the control flow and the call flow. It's a bit complicated data structures, but it's quite famous for representing the graph. And then they have their query language to run on this code property graph, and that's what we used actually to search inside the big amount of projects and to search for our testability targets inside.
Okay, thank you. That is really awesome. And how do you transform them? Can you transfer everything, or like, yeah?
So as Luca mentioned, that till the moment it's not really possible, or we don't have enough mature in this direction of our research to say, okay, how we can transform all of them. That would be very interesting for the community for the upcoming work, maybe to check more how they can to do the transformation. The five automatic transformations that we use them from the T1 type, which is semantic preserving, and that's help us to not produce a huge amount of false positive if we apply the over approximation. So that's help us to give a specific number of alerts, and out of these alerts, we could find we can find the true positive inside.
Okay, thank you for answering. And the last question, so how OWASP community can take advantage of your testability patterns?
Maybe I can take that one. So yeah, as we mentioned before, the patterns are already available. So if anyone wants to use them, he can do that. I would suggest again to come in touch with us, because there is an ongoing version. So the person could just get this ongoing version rather than the oldest one, the other one. However, we will definitely try to have this OWASP project to let's say advertise and to make our patterns more tied to the OWASP community. And we hope that by doing so, we will have more people, let's say, helping us in this work and perhaps making web application more testable for SAST at the end of the day.
Yeah, okay, for sure. Thank you so much. And the last question, so sorry, from audience that somebody has mentioned that I would be interested, what was the response from the commercial SaaS tools vendors, if any, regarding missing so many targets in the code?
So, okay, it's a good question. I mean, we are in touch, especially with those providing commercial static analyzers. And we had a few discussions in this respect. It's not something easy. I mean, some of those Tarpits do not require much work to be supported, I must say. And so, indeed, that can be pretty easy for some of these SaaS tools to, to release a new version where some of these patterns are supported. But something we saw is something we thought about very recently, is that for many of these tools, you can also provide what are called kind of modeling rules. So essentially, you can tell the tool how to interpret a function that they are not able to interpret at the moment. So that is something that is pretty interesting for us, because we have the pattern that capture a Tarpit that makes something difficult for the tool. Okay, we have the discovery rule, so we can discover this Tarpit inside the real application. And now what we could do, for some of them at least, is to provide this modeling rule that will tell the tool how to solve the Tarpit, so how to interpret the Tarpit. So that is not a Tarpit anymore. So somehow the one developing the Tarpit, creating the Tarpit, creating the pattern, can provide these three information. And by doing so, the tool immediately should be able to cover that pattern, to support the Tarpit, and so to increase the coverage and the testability of the application. So this is something we just started, and I hope we will have some results in that respect.
I hope, and I believe, I'm sure about that has totally answered the question. And thank you so much for this session. It was really wonderful and amazing to hear you guys. And shortly we'll be moving to the next session in another 10 minutes. So let's wait for it. Yeah.
Okay, thank you very much.
Thank you very much.
Thank you, bye-bye.
Bye.